Hi, good evening, everyone.
Good evening, sir.
So
Okay. So now this is the week 4, and I hope you have started watching the lectures. Okay. So before starting the session, anyone, any doubt, any specific doubt in week 4 content which you want to discuss in today? Any query from your side? Okay. How many of you have watched the lectures video of week 4? Can you raise your hand?
Sir, not all.
Not all. Okay. One. Nandan. Yeah, Nandan. Okay, so you just raise the hand. If you have any query, you can also ask. Okay.
I have not completed everything, but I'm the last. I've reached up to topological sort basically, and I've just watched all of it once and did the AQs. But so I have to
Okay.
go through it once more to sort of be perfect. Maybe read the notes also. So after that.
Okay. Fine. Okay, so if no specific query, then we will summarize all the things. Okay. So meanwhile, you can also ask in between. So raise the hand. You can speak. Okay. So let's start with the basics of the graph. So you know that this is the graph unit. Now we have started the non-linear data structures. So let me share my screen. Okay, so till now basic data structure we have already seen till week 3. Now the week 4 is now we are moving to the advanced data structure. So like this graph we have. Okay, so this is the first basic graphs, and in this week we are learning the basic algorithms which we used with the graph. Next week also week 5 is also related to the graph, but that have some advanced algorithm for some specific purpose. Okay, so start with the basic introduction thing. So as you know that before starting the graph, you should know how we represent the graphs in our data structure in our programming. So let me open this. Okay. So basic should so you should very clear about this representation of the graph. Okay, so like this is just like a logical representation, which we can easily understand how the nodes are connected to the another vertex, or we use basically vertex terminology. Node we generally use the graph terminology. But okay, so how our actually data is connected to the each other data. Okay, so that logically is represented like this. So here, according to the graph, any vertex can be connected to the another vertex. So there is no like proper hierarchy like as a tree. So here, so this is like a any random connection we can generate with the vertex. So this is the logical representation, but how we will represent this into our memory or in our data structures, like what data structure currently we have in our programming language. With the help of that data structure, how we will represent. Okay. So first thing, so basic, this is a non-linear data structure, as we are not storing the data in a sequential memory representation. Here data is stored at different memory places, and we are just connecting each data to another data by some reference or address like this. Okay, and that connection we called as a edge. Okay, those are logically what connection we are doing between two vertices. So that connection is represented by the edge, or vertex is simply a data. Okay, so you can see this logical structure. We here we have 5 vertices. So these all are 5 vertices. So the one second. So this A, B, C, D, E. These are 5 vertices, and these are the connection. So A and B are connected. Like okay, so B and C are connected. A and C are connected. So all these are connection logically. And to represent this, we use some representation. So this is just general basic representation, how we are representing the graph. So write like this. So G equal to V comma E. So this is means we have the set of vertices and set of edges. So we are representing the set of vertices like in this set. So we have total 5 vertices. We are giving some label, and edge we can represent it like some label also. We can mention some label for the each edge, or we can also represent it like this in the tuple format. So where the each this pair actually A B, this one pair is representing a one edge and representing the information that one edge connection is in between A and B. Okay, so this is a basic representation. And now you know about the vertices and edge. Okay, next things terms under the degree. Okay, so we will discuss basics terminology also regarding the graph, because many question I hope you have already seen activity questions or some basic questions also generate with the basic properties of the graph. So what is this degree actually? So degree is represented that how many edges are connected to the vertices. Okay, so there are two types of graph, basically undirected graph and directed graph. So undirected graph means there is no direction mentioned on the edge. Okay, so there is no direction, means where from edge is coming and going. So that is called as a undirected graph. If edge is represented, like direction is given on the edge, so that is called as a directed graph. So in the undirected graph, what is the meaning of degree is how many total edge are actually connected to the vertices. Okay, so that is the total of that vertex. But for the uh, directed graph, okay, so directed graph, there are two types of degree, like in degree and out degree. So in degree means, so if we have vertex A, so how many edges are coming to this? Okay, direction is like this. Okay, so direction is to the that vertex. So A, how many edges are coming to this vertex? So that is the in degree for this. And how many that edges are going outside of this? So that is called as a out degree. Okay, so total degree is in degree plus out degree, but we can also separate this with the separate in degree and out degree count. So this is the meaning of degree. Okay, path basically is a sequence of vertices connected by a edge. Okay, so that is like a if we have the graph A, B, C, D like this, and we have some connection like this. So we can say that our graph, we have the path from A to D. Okay, so A to D, we have the path, we can move from this, we can go through this. Okay, so there is one connection between these A to D. Okay, so this is called as a path. So we can consider as a sequence of vertices which are connected by some edges, or sequence of edges we can also consider as a path. Okay, here also simple path. This is one another thing. A simple path is a path where no vertex is repeated. So this is simple definition. One more thing, in our that course, we are using simple graph. Okay, simple graph means we will not use like a self loop. Okay, so this type of loop we will not use any algorithm or any questions or any place. And also we will not use the parallel edge. Okay, so that A and if B, these are, so only one edge is possible. There are two edges are not possible like this in the same direction. Or if it is undirected, so that means A, B, so only one direction is possible. We cannot represent like 2 or 3 direction between the same vertices. So this is graph means there is no self loop and there is no parallel edge in the graph. Then only we are working with the all algorithms in our complete course. So always think about that. These conditions are not exist in our any input graph. So cycle is a path that start and ends at the same vertices. Okay, so that naming is very clear here. Cycle means we are starting from some vertex, we connect like this. So if we are starting from A to B, and then D, then C, and then coming to A. So this is forming a cycle. Okay, now connectedness. So connected, yeah, this is also one important things. So our graph is connected or not. So a graph is said to be a connected if there is a path between any two vertices in the graph. Okay. Otherwise, it is disconnected. So if I say that we have a graph, so A and B, and here C and D, and okay. So this is a one graph. We are considering this as a one graph, but this is a disconnected graph. So here there are two component of this graph. This is the separate component and this is the separate component. So there is no path available from A to C or A to D or B to C like this. Okay. So but inside this component, one component, this is we are considering this is a connected. Okay. So A to B is a path available. Similar to second component, we can move E to D, C to E, or this C to E. All are actually connected. So yeah, so this is about the connectedness. So that's, yeah, our algorithm will check these things also, and this is also very useful real life problem scenario. Yeah, component, as I mentioned that, so that is represent connected subgraphs in the main graph. Okay. So as you know that the connected means what is the, okay, directed graph. Okay, so graph I have mentioned that where the direction, each edge has actually have a direction represented by an arrow. So that is called as a directed graph. Undirected graph, all edge actually do not contains the directions. Weighted graph where the edge also contains some value or weightage. Okay, some value we assign with the edge also. So suppose in the real life scenario, if we are representing our graph or some that map actually. Okay, so we are creating our some data, that map data structure where we are representing the so city to city connection by a road. So that what is the distance of road, that distance will be considered as a edge weight. Okay, so sometimes we need this to represent the edge weight. So that is called, if our each edge contains the weights, so that is called as a weighted graph. Next thing is adjacent vertices. Okay, adjacent vertices. Two vertices are adjacent if they are connected by an edge. Okay, so here we have the graph, if undirected graph. Okay, so this A, B, and C. So here, what are the adjacent of A? Okay, take one more. So what are the adjacent of A? So that adjacent of A are actually which are directly connected to this A. Okay, by a edge. Okay, so B and C are directly connected by a one edge. So this B and C are the adjacent, but D is not adjacent. Okay, so D is not directly connected. So adjacent of B, so that is A and D. Okay, similar things. If this is a directed, so that we check that where we can move actually according to direction. So here, what are the adjacent of A is actually B and C. What are the adjacent of B is only D, because this time not move from B to A side. Okay, so this direction is just like A to B only. So we cannot say that this A is a adjacent of B. There's no direction for the B to A. So in this way, we check the adjacent vertices. So where edge are going in the directed graph, we consider direct edge. If connection is there, so that we will consider the adjacent vertices. Okay, incidence. A vertex is incident on an edge if the vertex is one of the endpoints. Okay, of the edge. Okay, a vertex is incident on edge. If the word. So this means okay, a vertex is incident on edge. So what vertex actually connected on the edge, that is called as a incident. Okay, so here you can see, if we consider that this is a E edge, so what are the incident of this E1 edge, so that A and a C. So okay, and so here we are just looking through the edge side. So what are the edge actually that vertex are connected on the edge?
So
Okay,
is B incident of A or D?
in directed graph. Okay, one second.
B is adjacent of A because there is a path from A to B, but A is not adjacent of B because there is a no direct path from B to A.
No, incidence is
Incident.
separate. Incidence is separate thing. So yes, sometimes we also represent the incident matrix for this. Is represented like this. So if you have graph 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. So here also for the directed graph we mentioned that where edge is coming. So that suppose if A and suppose we have 0 to 1 edge. Okay. So this is represented like this. So we take like as a this is coming from 0. Okay, so we just consider as a minus 1 on the 0, and it is going to the 1. So here plus 1. So that incident, this edge is incident on the both. Okay, but the representation will look like for directed graph like this. Okay, so minus 1 means we are this is the outgoing edge from 0, but one side this is incident on. So here we can consider that as an incident from or incident. Okay, but this edge is connected to the both actually.
So why this -1 representation at 0, 0?
No, this side actually vertices. Okay, 1 second. 0. That no, so this matrix is not written like this. This is written like some edge basis. So we also consider that E1. Okay, that is different. So that is like 0. One side we represent as a vertices. Another side we represent as a edge. E2, E3, or like this. Okay, and then we write like this. So -1 and +1. Okay, so here this is representing E1 edge incident from this is 0 and but incident on 1. So this is like a one representation based on the edge actually. So if we are considering the edge and connecting to on the vertex. Okay.
Okay, sir.
Hmm. So okay, so next thing is subgraph. So subgraph is a subset of another graph with some edge and vertices removed. Okay, so this is just like a subset of the graph. And complete graph, yeah, this is also important. So complete graph means where all vertices are connected to the all vertices. Okay, so suppose we have the graph like A, B, C, and D. Okay, so like this, A will be connected to the all three vertices. Okay, not this like okay. So A. Similarly, this C will be connected to the all remaining three vertices. Now D will also connect it to the all vertices, and same for the B. So this is look like a means every pair of the graph have direct edge. Okay, so this is a complete graph. Okay, so yeah, so some basic question also ask for this, like how many edges are possible in the graph? If suppose if we have 4 vertices, then how many total maximum edges are possible for the complete graph, or how many maximum edges are possible in? So like this. Okay, so complete graph actually contains the maximum possible edge. If you have 4 vertices, so this is the situation when this graph has a maximum number of edges. So here the direct formula we use like this is a like n, if suppose n is the number of vertices, so we use n minus 1 divided by 2 for the undirected graph. Okay, so you can remember this formula to calculate the total number of edges directly for the undirected graph. Okay, so here 4 you can put here, so 4 into 3 divided by 2, so this will become 6. So total 6 edges are possible. So if suppose this question is asked for the 10, you can directly calculate it from this. If this is a directed graph, so directed graph case, 2 edges are possible between each pair. So that is like suppose this A to B and B to A, like this. Okay, so here the this will be increased by twice. So here that means if we will remove this part from the formula, so this become a formula for the graph. Okay, so what are the total maximum number of edges possible in the directed graph for given vertex? So you can directly calculate it from this. So 4 into 3 total. So these two formula you can remember for this maximum number of edges. Minimum number of edges is possible if graph is connected, so that is n minus 1. Okay. So if graph is connected, so we have 4 vertices, and that is connected actually. Connected means there is a always path available ECD. So that means this is the possibility that for the minimum connection 3 edge. So these are some basics. Now this is the logical representation for directed graph. You can see this is so the undirected graph, unweighted looks like this. Directed and weighted like this. Only directions are there, and here weights are available on the edge, but directions are not there. So this is undirected and weighted graph. This direction and weights are also given. So directed and weighted graph. So this type of graph we will see in the upcoming all algorithms or all problems. These are the different type of category. Now comes to the representation part. So how this data is actually represented. So there are two ways to represent this graph. Is first is adjacency matrix. Okay, so this is like a similar to your matrix form. That means two-dimensional representation. So row and column combination. So this we can represent either two nested list. Okay, if you are using Python, that means you can use a Python nested list. Okay, so that means one list, and inside this the values are another list like this. Okay, so this nested list considered as a matrix form. Otherwise, you can also use a NumPy array in 2D, NumPy 2D array. Okay, so professor have used this 2D array also in the lectures. So, and another form is adjacency matrix. Okay, adjacency matrix, and this adjacency list. Okay, here in the conceptual form, this is actually a type a linked list. This adjacency list means it is type a linked list where for each vertex, suppose we have a graph like this, A and B and C. Like suppose this is the graph. So how we can represent this as in the form of adjacency list? This list means is not a list. This is like a linked list. So for each vertex, we make as a starting vertex like A, B, C, D. Okay, and then we link to a linked list. Okay, so where each node actually contain the adjacent of this. So A to B is direct connected. So we will store one node in one. A to C is another. So that means we will connect another node in the second node. Okay, so in the linked list. So C, and this is the end of the linked list. Okay, similar B. So B adjacent is A. So one node will be connected to this. So that is A, and this is the end of this linked list. C is connected to two nodes. So two node will become in this linked list. So this is A, and this is D. Okay, and this is the end point. Is connected to C, so only one point. Okay, like this. So this is like a for each node we create a linked list, and that represent the adjacents. So A have two adjacents, and this information of two adjacent is stored in this linked list, which is connected to A. And same for B, same for C, same for D. So this is the structure actually for the adjacency list. For Python, we can also direct. So we can also write this implementation with the help of Python dictionary actually. Okay, so here why this is useful, because we can directly identify that which actually vertex are adjacent of which another vertex. Okay, so if suppose if we required like what are the adjacent of C, so we will directly look into this C vertices linked list, and we will directly get the list of all adjacent of this. Okay, without checking the another vertex. This representation we can implement with the help of Python dictionary. So we can make this as a key. So for each vertex, we can make as a key. Inside the value, we can consider as a list. So B, comma C like this. So that we are making in our Python implementation. Okay. So values are only list of adjacent. So A, D. So similarly C. Okay. So you can also directly access. Okay, so you know that dictionary we can directly get this information. So suppose if we want to identify that what are the adjacent of D, we will directly check through the key, and we will get a list of adjacent. So same things, so same purpose we are implementing through the Python. this linked list, adjacency list representation. So these are two implementations. So for unweighted graph, you can see this is the general implementation of the graph, and for matrix now. So this implementation I have included in the notes, so you can see how we can create a adjacency matrix, okay, for any given graph information. So this is the vertex information, this is edge information given, and this is a like a one undirected graph, okay, undirected graph. So here numpy, actually we use the numpy. So we are just creating the what is the total number of vertices so we have created a matrix, zero matrix of size. So 5 by 5. Total 5 vertices are there. So 5 what is matrix that we have created, that is actually zero matrix. After that we are traversing each edge and we are looking. So this first value will represent like a, the second value represented like as a column, okay, label. 0 to 1, that value should be filled by 1 if edge is there, otherwise 0. Okay, so you can see this is like a matrix for, so here each like this 0 1 2 3 4 and same 0 2 3 4. So now this cell value is representing the information of edge actually, okay. So this side like as a row and this is column. So key value is 1, suppose this is a 1, so this is representing a edge from 0 to 1 vertex, okay. Okay, so same if suppose this is a 1, so this is representing edge of 2 to 3, okay, because this is undirected graph, so entry will be come from both sides, okay. Okay, this is undirected, 1 second. Oh, this is a directed, sorry. Okay, this is a directed graph, so entry is coming from only that source to side. So here you can see if edge is there, so suppose this this edge is there, so 2. So this is this row will be considered as a source and column label will be considered as a destination for the directed graph, okay. So 2 to 3, so 2 to 3 means this edge actually, okay, but 3 to 2 is not there, so you can 3 to 2, there's no entry here, this is 0, there's no edge. So this entry represented as a edge information. If one value is there, so that means row to column label is there is one edge, okay, otherwise 0 is there, so that means no edge. So same things you can also maintain by the Python nested list. You can make a simple list and inside that create a row or and append into the main list. So this is the same things, but we are creating this with the help of Python nested. So same type of structure you will get a one main list. Inside that we have the sub list, okay, and that represent the each row, okay. So say if this value is 1, that means edge is there from I to J. Now the for adjacency list representation, as I mentioned that here create a dictionary. So this is the dictionary, and for each vertex, okay, for each vertex we create an empty list as a value initially. After that, if edge is there, so we just store this information. So 0 to 1 edge is there, so we will append this into a inside the list member, so that 0 is a key, and inside this value list, so 1 is the source listen, so we will append this as a 1. If 0 to 2 is also connected, so we will append here this 2, okay, and nothing is there, okay. So same things for the each 2. So this will become a adjacency list, okay. So this type of representation is called as a adjacency list. Same things we can do for the unweighted undirected graph. So here representation will be come from both actually. So any edge like 0 to 1 is given, suppose for undirected graph. So that means 0 to 1 and 1 to 0 we will consider as a both as. So entry should be there for both sides. So 0 to 1 and 1 to 0, both sides in our table, that matrix. So that will become a that undirected graph. If we are making as an undirected graph, so each edge will be represented by 2 entry in the our data set, okay. So same things here you can see. So each edge like 0 1 2 3 4 0 1 2 3 4. So here this entry 0 So 0 to 1, and same you can see here 1 to 0. So the second entry is corresponding to this one. So each entry will be represented by two entry, okay, by putting one. So this is adjacency matrix, and this is using Python nested list. So same thing we can create as a nested list. So here same for the nested list. If any edge is there 0, 1, so that means this will come like this. Same for this. Okay. So 0 key, and the value will come as a that adjacent vertices, and same for 1. So 0 will become as a adjacent vertices. Because there is no direction, so this will be considered as a two entry in this. So now this is all representation. Python dictionary, yeah. So this is all about the basic of the graph representation. How we like represent our. We will always think about logical structure, but our data will be available in our this either matrix form or adjacent form. Okay, our code will work with these data structure. Okay, but our imagination should be for the logical of a structure, how we are moving to the another vertex or adjacent vertex like this. Okay. So any doubt till point?
No, sir.
Is
So,
path and this walk same thing? Like because we defined a simple path in the definition a bit differently, like without repeating any vertex.
Uh, Path or walk.
Yeah.
Mm, this is just a different terms actually. But what terminology we are using? So walk is like if and destination are different, so that is become like a path also. But if we are coming back to the same node, so that will become like cycle. Or in walk, we can also repeat the vertex.
Hmm.
So there are some traveling salesman problem. There is one walk actually, like we need to traverse all the vertex, and after that we need to come back to the main vertex. Okay, traversing all the vertex like this. So this is actually just like a terms difference and use case how we are just using this word.
Okay.
Sir,
Hmm.
how it is different from the we are reading maths one, the 9 and 10.
So this you are saying that this graph how it is different.
Ah, yes,
No,
the graph.
this is not different. I think this is the same. So I think you have seen this in the math as well as the CT, if I'm not
Ah,
wrong.
yes, yes, sir, yes, sir.
So this basic graph data structure you have already seen in the previous two courses. But at that time, I think you have already only seen the data structure represent, or maybe I think you have already seen this BFS and DFS also. But at that time, you have already seen only the algorithm steps.
Uh,
Yes, sir.
Now
Not
here,
coding part is
everything.
involved.
coding part you have not seen here. So here we are just also using this in the implementation as well as the problem solving.
Okay, sir. And the array linked list is done. Like it is only from in a
That
one week.
that's our basic data structure that we will use to implement the other data structure now. So you can see here for representation of the we are using the list as well as the dictionary. So that's our actually basic data structure or that provide by the programming language. So in a language like C provide the array, Python providing the list. Okay, so that are basic data structure, and generally we consider also as a linear structure. Okay, but these are the non-linear data structure, so that we can implement through the linear data structure.
Also, we should remember the code of that, like sorting and the linked list. It should be help or what should we do?
No, so what you have learned in the previous week, definitely that will be helpful to understand the remaining coming week concept. Okay, so if you have understand the dictionary concept in the week 3, so that dictionary concept is now we are using inside the adjacency list implementation. So you know how dictionary is implemented. So that's our basic data structure. I hope you have already used these basic data structure in your Python course also. Okay, the dictionary you used, Python list you have already used. Now that data structure we are using to create another data structure. Okay, just we are representing our that information with the help of basic data structure. So same things like link, we have understand that. So some place you will also see that we will use the linked list type of a structure. Okay. So as I mentioned that the adjacency list basically a linked list actually, but that we can implement directly through the dictionary in Python. So same complexity we will get to perform the operation to insert or access the adjacent information. So we are just using that implementation. Okay. Okay. Any other query? Otherwise,
No,
we
sir.
will.
Thank you, sir.
No, sir.
Okay. So before entering to the direct graph algorithm, so that the previous part, prerequisite part I have discussed, so that should be very clear because now we will directly use the our representation. So you have already seen in the prof lecture. So prof lecture have discussed each algorithm with matrix also and with the edge list also. Okay. So there is only minor change in the algorithms will remain same, only the implementation will become different because we are using the different data structure. So how we are getting the same information with the different data structure, so that part will only become actually change in the coding. Now the comes to the basic algorithms of the graph. So like you have already seen these algorithms initial previous two courses. So same algorithms. So these concepts same. Okay, so nothing is changed. So now first thing, these are two traversing algorithm. Okay, traversing means we want to visit the data which is stored in the graph representation. So that you know that we have already discussed linked list concept. So we have the head. Okay, so this head contain the reference of the first node. Okay, now the all nodes are actually connected by reference like this. Okay, and these all nodes are maybe stored in different memory locations, but we are maintaining the relations by address of each node, and we are connecting in this logical representation. So if we are storing only head information after storing our data on, after that we have only head. Okay, and with the help of this head we can get complete all data by traversing by these connections. Okay, and we will just visit all the data information, okay, in this structure. So same things here also, your graph now, your vertices is connected like this form. So like this is connected 1 to 2, 2 to 3, and this form node vertex and edge form. Now you want to traverse, suppose you have the graph with this information and this, you want to traverse each x actually. Okay, uh, through these connections. So how you can traverse? So these algorithms are basically the purpose here for the traversing the each vertex in our this graph data structure. So these are the different way to traverse. The purpose is same, but the way is different. So these are the two different algorithms to performing the same task. So BFS, at first search. Okay. So this BFS actually used to traverse a graph or a tree. Okay, so that tree is also we can consider as a graph. So both type of data structure can be traversed from this BFS. But the concept of this traversing is so we will always traverse the adjacent node first. Okay, so we will, if we can start this BFS from any vertex in the graph, but after we will always complete the traversing of the each adjacent of that vertex first. Then we will only move to the next adjacent. Okay, so what's the meaning of this? So suppose if we have, I'm just making this type of a structure. So the This is similar to your tree structure, E, A, B, C, D, E, F. Okay, so suppose if we are starting the BFS from A, so for traversing, first node is traverse this A. After that, all adjacent vertices. So what are the adjacent vertices of this A is C and D. Okay, so this C and D should be traversed first before moving to the next level. Okay, so this is a next level. Like this is not directly connected to the A. So after traversing A, we will complete all the adjacent of this A first. Then we will move to the next adjacent level. So that we will check for the adjacent of C. Okay, then we will traverse. Then we will check for the adjacent of D. Okay, so that means here traversing is happening adjacent level wise. So first complete all the adjacent node first, then move to the next adjacent levels. So this is the concept of BFS. So like if suppose the graph A, B, C. Suppose graph now. Now this is not a tree form, and here we are Yeah, Prasant.
So my question is why we are not using the binary search in that?
Binary search?
It is also a searching algorithm, no?
No, no. This is not a searching algorithm. This is a traversing algorithm. Search here we are not searching any vertex actually. Here we are traversing each in the graph.
In
And
a
also this is not a linear data. This is non-linear data. You don't know where you need to move actually, where you can move, because the connection may be happening between any vertex.
oh, okay.
Okay. Binary search is applicable only the sorted data. If your data is sorted, then you can apply the binary search. Yeah, there is one data structure you will see in the Week-6 that is called as a binary search tree. So where the concept is very similar to your binary search, because we will maintain our data in the sorted form in our tree structure. So then you can apply that binary concept. Okay, so that we will see in the Week-6. But this is a non-linear data structure. So here actually, and these are the traversing algorithm. That means we want to traverse each vertex which are available in this graph. Okay, so how we can do this task? So suppose in this graph, so A is the first vertex we have traversed. After that, which vertex should traverse? So that means what are the adjacent of A? What are the adjacent of A is here?
B and C.
B and C. So after traversing A, these two vertex should be traversed. Okay, either you can traverse C or you can traverse B. Conceptually, we are not looking the in this, but implementation will follow some order. Okay, but conceptually, the BFS says that traverse the adjacent vertex first. Okay, so that means after traversing A, we will check what are the adjacent of this, and we will traverse B and C. So once the B and C traverse done, then we will move to the what are the adjacent of B, and then what are the adjacent of C. Okay, so we will complete like this. So A is the first vertex, and now we will traverse adjacent B and C. Okay, this is completed. So this level is completed. All adjacent of A are now traversed. Now we will look for what are the adjacent for B. Now, okay, so B adjacent is A and E, but A is already traversed. So if we have done it, we have already traversed, we will not check again. So what are the not vertex which is not traversed? Okay, and which is adjacent of B, that is E. Okay, so that means E will be traversed after this, and now check for the C. Okay, we will not move to directly for E because here the label is not completed. Okay, so C adjacent of C, A, E, D. Okay, but E and A is already traversed, so D will be traversed. So this is the label wise traversing. So you can see A is traversed first. The adjacent of all A is now traversed. Now adjacent of all and C will be traversed on the next level. Okay, in this way traversing is done for the each vertex. Okay, so this is the concept actually. So now you can many questions in the exam comes for this type of concept. So no need to remember any code for this, no need to remember any implementation or like full complete pseudocode for this. Apply this concept on your question. Okay, suppose if any graph is given, let me check. Ha, Saraswat, yeah.
Sir, as it's given that the worst case of BFS is O of V plus M
Hmm.
in adjacency list. So
Hmm.
how was the analysis of it? Like, which is the worst case? Like, when all nodes are connected to each other, or it's a single edge connection between each node? Which will be the worst case for
Okay, so
breadth first?
that's we are coming. How we are considering this that complexity, so that we will only look after the algorithm, after the algorithms. Okay, so first we will discuss the basic concept. So now suppose this graph. Okay, I have just picked this one graph, and now in the exam also this type of one graph suppose is given, and asking that what is the correct order of BFS algorithm if we apply on the fourth vertex BFS. Okay, so some wrong option will be given, and sometimes some condition is also given. If two adjacents are there, then algorithm will always traverse the vertex which have the level value. So that I just follow the each condition which is given in the question statement. Otherwise, conceptually, okay. So if I am starting the on four vertex, okay. So this is the four vertex is traversed first. Then we will check what are the adjacent of this four. So adjacent of four is 3, 2, and 1. Correct?
Yes, sir.
Yes, sir.
Okay. So conceptually, this can traverse in any order. Okay, because all are actually adjacent of this four. But if you will see the implementation or any specific implementation where we are using some specific data structure, so that will follow some actually way to traverse. So maybe that algorithm, that implementation follow either the incremental order. So how our data is stored in our memory. So after when we are looking for the adjacent of four, so at that time, so you will apply some logic for that. So if data is available in adjacency list, so how the adjacents are stored in adjacency list. So suppose if it is stored in adjacency list, so like this 1, 2, 3. If suppose the adjacent are stored in this way, so your implementation will store first 2 seconds, then this one. Okay, so this order will be fixed for the implementation, but conceptually uh, you can traverse any adjacent. So here we can write like this. So suppose if I'm traversing 1 and then 2 and then 3. Now these three vertices will be traversed first. You can write like order 4 and 1, then 2 and 3. Okay. So after that, this level is completed, then we will check for the next level. So what are the adjacent now? Okay. So adjacent of 1 is 0, 3, 4, but 3 and 4 is already covered. 0 is the new. So 0 is coming on this level. Now it's 2. So 2 is already connected with 3, 0, and 4 all done. Okay, what are the adjacent of 3? 3 adjacents are 2, 1, and 3 done. Okay, so now this is the order actually. So 4 is traversed first, then these 3 nodes are coming, and then this is coming at the last. So to validate the answer, maybe some wrong option will be given like this. So 4, 1, 0, 3, and 2, like this. Okay, so this is not, because 0 cannot be traversed on the that second level. Okay, 4 if we are considering this as a first level, and so 0 cannot come this level because 0 is not the adjacent of 4. So without completing the adjacent of 4, all adjacent of 4, we cannot directly traverse the vertex which is not adjacent. Okay, so this cannot become here. Okay, so you can figure out this type of questions in the exam. So it's, for the graph is given, just identify that which traverse is BFS traverse is correct for this. So just look this how the adjacents are completing. Okay, which option is so that type of question mostly checked by the options. So just check which actually order is following the correctly BFS concept. Okay, and then identify the answer.
Sir,
So
but given a, excuse me, sir, given a tree structure like the one you have drawn, it's only sort of the alternate level where the edge won't be there, right? So if you go the other way around, so from four, there is a, you'll obviously have an edge up to 1, 2, and 3, but there is also a chance that you'll have an edge from 1 to 3 in this case, right? But given a tree structure, we can also state that you can have an edge from 1 to 2 also, no? But 4 to 0 is not possible.
okay, so what tree structure you are making? Let's suppose if
No,
I'm
no,
creating
no.
one.
So let's consider the given tree structure only, the one you have drawn. So from there, so I mean, in the AQs, for example, there was a question that given the tree structure, uh, uh, what are the edges from
Okay,
various
okay,
nodes
okay, okay, okay.
which
I'm
will connect to the
okay
way.
getting your
So
point.
yeah, so I thought from 4 you could have an edge to 1, 2, 3, which is very obvious. 4 to 0 you won't have an edge, but
Hmm.
considering this graph, you have an edge from 1 to 3, right? And
Hmm.
now that we know the graph, we know there is an edge from 1 to 3. But if suppose we don't know the graph, which naturally the
Hmm.
question won't show us the graph, then we can also
Hmm.
assume there is an edge from 1 to 2, right? If you're at the same
Hmm.
level, so we can assume that there is an edge, right? I mean,
Huh. Okay. So I got your point. Which question you are pointing out? Okay. So actually, after traversing, we are getting this type of tree structure. Okay. So each this traversal algorithm generate the tree. Okay, and for some activity questions, this type of question is given. So suppose this is a tree generated by the traversal, either BFS traversal or DFS traversal. So
correct.
what are edge which is not possible in the original graph? So that type of question is given in the activity question, and that type of question is also asked in the previous terms exam. So how we can identify this? Okay, so for BFS, here we are talking about the BFS. So in the BFS, um, so the logic is here because if our edge is given like 0 to 4, okay, so 0 to 4 edge is there, suppose if original graph, so that should we come into the this first level, not into the second level in our tree. Suppose if we are saying that 0 to 4 edge is possible in original graph or not. So that is not possible because if suppose 0 to 4 is in the original graph, so that once we will traverse the 4, so 0 should also be come in this level because 0 is the adjacent then. That cannot be come in the next level if this edges are there in the original graph. But here suppose if we are talking about the 0 to 3, so here yeah, that is possible in the original graph because you have already seen the 0 to 3 0 to 3 0 to 2.
There is no
Okay,
0
so
to 3, no?
hmm?
There is no 0 to 3, right? There is
no
1 to,
no direct edge is there.
no direct
0 to
edges.
2 is huh.
Yeah,
So 0 to 2 is there. So yeah, if you connect 0 to 3 also, then still you will same type of tree. Okay, because how it is possible that because here this is not a adjacent of 4 directly, so definitely if it is adjacent of G3, still it can come on the next level because what are the adjacent of currently 4 we have 1 3, so that means these vertex can directly connect it to the 4 1 2 3. So 0 to 2. So here I am just giving the direct hint. So distance actually, and distance between a root, actually root or any vertex. Okay. So suppose if we are talking about U and V edge, so this is exist or not. So here the logic is distance from this root to U and root to V. The difference should not be minus d to v. This only possible is 1 absolute value. So this distance from root to u and distance from u root to v. So distance you can either calculate like this. So suppose if we are talking about 0 to 3, 0 to 3 is possible or not. Okay, 0 to 3 is possible or not. So what is the distance from 0 to 3 root to 3? So root you can if you suppose if you're counting the distance by number of vertices in the path. Okay, so that means distance is 3 for 0. Okay, and what is the distance of this 3 vertices? 2. Number of vertices are coming in this path 2. So that's 2. So that if you calculate the absolute difference of this, you are getting 1. Okay, so that means if this difference is 1 or less than 1, like 0, then that edge is possible. If this difference is coming greater than 1, like 2, 3, then that is edge is not possible. Okay, that not possible in the original graph, because then label will be changed for the this edge. Actually, if this difference is more than 2, suppose if u and v here, if we are talking about in this case 0 and 4, so the this 0 distance is 3 and this 4 distance is 1, you are getting 2. This is not possible, because if this is possible, then this 0 cannot come on this level. This should be come on the previous level. In BFS case, we are traversing our nodes adjacent level wise. So that means our difference is possible only either 1 or 0. 0 for the same level. Okay, so if you suppose edge is there 1 to 2, so the distance difference will be 0. Or distance is possible on the only one single distance, single level difference.
So
Okay.
1 to 2 and 2 to 3 is possible. An
Yeah, 1
edge.
to 2 is possible, 2 to 3 is possible, and also
And
the
one
next level 0
and what
to
about
2, 0 to 3.
no, what about 1 to 3? In the original
1 to
graph,
3
1
is
to
also
3.
possible. 1 to 3 is also possible.
So basically anything on the same level is possible. We can all say
Ah,
they are directly connected. The edges are
yeah,
connected.
same level.
But
So that, as I mentioned, that the difference of the level should not be greater than 1.
okay, got it.
Okay. In the BFS case, difference of the level cannot be greater than 1 for any edge. If it so that edge is not possible in the original graph. If that difference is more than 2, or sorry, more than 1, so that edge cannot be come in the original graph. Otherwise, that vertex will should be come on previous level in the traversing, because according to the nature of this BFS. Okay. So this for BFS question, you can remember this concept. If we are looking this type of question, so when we are checking this edge is possible in the, because this is the output. Okay, traversal output. This is the tree. So we are looking that this edge is possible in the original graph, because graph same type of tree can be generated from multiple graphs. Okay, so here if we connect 0 to 3 also in this graph, we'll get a same traversal tree. Okay, if you connect 1 to 2 also, then still you will get the same traversal tree. Okay, so but if you connect this 0 to 4, then you cannot generate this tree. Your traversal tree will become, so after this 4, you will get all 0, 1, 2, 3 at this level. If your 0 are directly connected. Okay, so for this question, you can validate your answer by just check the difference of the level of the S. Check what is the level number of 0 and what is the level number of 4, and check the difference. If it is coming greater than 1, that is not possible. If it is coming 1 or 0, it's possible. Okay.
So do you mean like reaching the point is not possible, or what?
Not as I mentioned that. Okay, I remove this. This is the main thing. One second. Here we are not checking the reachability. Okay. So as I mentioned that BFS algorithms traverse the node adjacent node wise. Okay. So if we are starting from 3, so after 3 we will traverse all the adjacent of node. Okay, on the next level. Okay. So 3 is starting now for the 3. So 2, 1, 4. 2, 1, 4. Next level, all these node will come. Okay. So this is the next level. Now to the move to the next level, so we will check what are the adjacent of 2, what are the adjacent of 1, what are the adjacent of 4. So that all nodes will come on the next level. So here level is representing the how much actually so okay, what is the path difference, or we can see that what is the distance from the 3 each has. So that this is suppose level 0 and this is suppose level 1, this is level 2. So this is representing like from 3, all these which are coming on the 2 level, that has 2 edge difference, okay, that are not directly connected. Okay. So here 0, so let's so next is 0 will come. So this is representing some information like this. So 3 and 0, 0 level is 2 and 3 level is 0. So that means 2 level difference. That means this 0 is connected to 3 by some path with 2 edge. Okay, not the direct edge. The first level which is just coming after this adjacent 3. Okay, this level is representing that all vertices are directly connected to 3. So based on this information, so for this input graph, this is the one input possible graph, we are getting this traversal order, okay, traversal tree by the BFS algorithm. But same type of traversal tree, you will get another possible graph. So you add this 2 and 1. Okay, so if you add this, still you will get a same traversal tree. Okay, this 2, 1, 4 will come on level, 0 will come on the next level. Maybe there is a chance that 0 will connect with some another vertex like 1 or something based on the implementation. But 0 will definitely come on the this 2 level. So this 2 and 1 is not affecting the final output. 1 and 4 for this graph, if we connect, so 1 or 4 is already connected. So 2 and 4 suppose yeah, this is also connected. Okay. So 0, 0 and 1, suppose 0 and 4. Okay. So if we will add this edge, still your output will not impact for this tree. Okay. So this time we are looking by this 3. Okay. So we are applying that traversal on the 3 vertex, not the 4. So still your output will remain same. This is the output. Because the distance still is 3 and 0 is path to edge path actually. So this is the validation for this type of question. So you can validate like this, level difference so cannot be greater than 1 if your traversal tree is representing a BFS. Okay. Okay. Okay, so the BFS, this is the concept of BFS to maintain this information. So because we are just traversing adjacent wise. Okay, so if we are starting from any vertex, like in this tree, this 3, suppose if we are starting 3, so we know what are the adjacent of this 3. So that is actually 2, 4, and 1. The other adjacents. So this will be traversed next. But to maintain the next level, so we will check all these 2, then 4, then 1. Okay. Then we will get the next level. What are the coming on the next level? So that means our checking should be done on the each adjacent 3. Okay. We have completed because this is the starting vertex, this is a single vertex. But the next level we have 3 vertex. So our should be come on the each vertex for the next level. So that means we should check what are the adjacent of 2, that will come here. Okay, what are the adjacent of 4, that will come here. What are the adjacent of like 1, that will come in this level. So all nodes, all adjacent of this 2, 4, 5 will come on the next. Okay, then we will move to the next level. So what are the adjacent of all these levels nodes? So that will come on the next level. So to maintain this, so BFS algorithm use a queue data structure. So first we will complete the all test checking on the all nodes of the current. Okay, then we will move to the next level. Okay, we will not directly moving to the without checking the previous level. Okay, so to maintain this proper checking, we use the queue data structure. So what we will do for this type of structure, so suppose we are applying this as a one vertex and adjacent of one is 2, 3, and 4. Okay, this. So this is coming on this next level. Next adjacent level will be check from this 2, 3, 4. Okay. So what we will do, we will use a queue data structure for this. So first we will insert one vertex into the queue, and so you know the structure that what is the property of queue? First in, first out. Okay, correct.
Yes, sir.
So we are inserting first into the queue, then we are checking what are the adjacent, and then we will remove this vertex from the queue. Okay, once we will remove the vertex from the queue, then we will what are the adjacent of one. So adjacent of is 2, 3, and 4. Now we will traverse each vertex and then we will insert these vertex the queue again. Okay, so queue we are maintaining something. So what are the adjacent of 1, 2? Okay, then 3, and then 4. We will insert all the adjacent of 1 into the queue. Now once this traversing is done, now we will just remove a one node from the queue. So that is actually 2. And we will repeat the same process. So suppose adjacent of 2 is like 5. Okay, so 5 we will traverse, we will enqueue that 5 into the end. Okay, in this, so that means we have checked for the 2 and we have traversed what percent of this 2 that, and we will insert that into the queue. So that checking for the 5, okay, that will come after completion of the all previous vertex. Every time we are removing one vertex from the queue and we are inserting all the adjacent in the queue at the end. Okay, we will check for the 2, then if it's done, then we will check for the 3. So 3, what are, suppose the adjacent of 3 is 6 and 7, so that 6 will be inserted into the queue at the end. Then we will check what are the adjacent of 4. Suppose this is the 8, so 8 will be insert here. Okay, so you can see here that how we are checking. So first we checked for the 1, then we insert all the adjacent of in our queue. So 2, 3, 4. So that means all adjacent which are connected to the 1 is now checked next. Okay, so 2, 3, 4. And what are the adjacent of these 3, 4 now all have added into the queue. That will be checked after completion of this level. Okay, so then 6, 7, 8. If any next adjacent levels are there, so that will be inserted into the bag. So in this way, we will maintain our checking level wise. So that means if we have checked 1, so all 2, 3, 4s are now added into the next level. Then we will check for the each vertex on that next level. After completion of this all vertex checking, then only we will move to the next. So that is maintaining by this queue concept. So BFS conceptually this use this queue data structure to maintain this level wise ordering. Okay, adjacent level wise ordering. So this is the default data structure which is used by the BFS algorithm. So now if you see this, so because of that is also discussed in the previous speak. It now comes to the like code. Okay, here. You can see. So what information is required according to the concept? What information is required for the BFS algorithm? So we are traversing our node. We need a adjacent information of the node. So what are the adjacent nodes from that node? So this adjacent, or sometimes we call it the neighbors. This information we required from our data structure. So what graph is represented either in adjacency list or in adjacent matrix. So this adjacent node information is required to process. So okay, so now you see this queue data structure is already added in the implementation because we need the queue and BFS. So here we are using adjacency list. So list, you know that each vertex has the column like 0, 1, 2, 3, 4, and we have the all adjacent information in list. This information. Okay, so neighbor information we can directly fetch through this. What are the neighbors of this two? We will get the list from here directly. Okay. So here, so what we are doing actually, you can see visited equal to empty vertex. This dictionary we are maintaining for the output because we will mark which vertex is visited or which is not visited. Okay, we will not visit the same vertex which is already visited. So now initially we are setting visited equal to false. Okay, I'm making some small graph for this. I think that will be easy to see. So suppose we are applying this BFS on A. So you can see start vertex we required for this algorithm. Adjacency list contains this graph data in the dictionary format. Now initial step is we are marking visited equal to false for each vertex. Okay. This is the first initialization steps. So this is this part initialization. Now we are creating a queue. So this is just object of the queue class which we have already done. Now we are setting the first start vertex because this is the starting point that we are marking as a true. So that we are marking as a true. Now we will repeat our process. So what we will do while our queue is empty. So we have marked this our start vertex as a true and we insert this start vertex into our queue. So we are maintaining now a queue and initially inserted into the queue. Okay, this. Every time queue we will insert from the end and we will remove from the first. So okay. So visited so after that we will repeat the process. Every time we will remove one vertex from the queue and we will check what are the adjacent of that which are not visited. If any is not visited, then we will insert that not visited vertex into the queue and will mark as a visited. Okay. So this we are following in this part. So we are removing one vertex from the queue so that first time this A will be removed. Okay. Inside this condition. So this is called as a current vertex. After that, we will mark this as a so we are marking for the edges. So after because we have already marked this as a true because it's the first. And after getting this, we will check what are the adjacent of this A. Okay, you can see for AD vertex in A list current. You can see what we are doing. We are just calling this dictionary and passing this current vertex as a key. So this will return a complete neighbors list. Okay, of this current vertex. So that neighbor list is B and C. Okay, so this first iteration that B and C, this will be done. Now this is just a loop reading the value B. Okay, we are checking not visited. Okay, this is visited or not visited in our dictionary, visited dictionary. So this is still false. If this is false, we are marking this as a true. Now that means we have visited this. So now B is marked as a true in this graph logical structure. Marking this as a true now. And after marking this, we are inserting this into a queue. So this is now removed, and from this side, B is now inserted. Second iteration. Okay, second iteration. Now C will be fetched, and C is a we will check first. Okay, this is visited or not visited. If not visited, we will mark as a visited, and this will also insert our queue. Okay. Now the while loop will iterate again because still queue is not empty. Two vertex are there. So then we will fetch again one B. So B is now fetched. as a current vertex, we will check what are the adjacent of B. So A, E, D. Okay, so A, E, and D. These are the three adjacent. This will be written by our data structure. So this A is already visited now because you can see this is already marked as a true. So we will skip this. So this condition is not satisfied. Now E, this is not visited yet. So that will be, we will enter inside this condition and we will mark this as a true. So this will become a true. Okay, and now this E will be inserted into the queue also. V is removed, but E will be inserted. Now we will check for the D. So D is also not visited, so that we will mark visited. So that also mark visited, and then D will also insert into the queue. So in this case, so now this is iteration is done. Okay, now we have checked same things. This is already done. Now we will remove C, and C adjacents are A, D, and E. Now you can see all are traversed. So this loop will run like as a without effect. So that A we will check. This is already visited. Already visited. E already visited. So now this is checking done. So you can see checking is done by first initially at the A, at the next level B and C. So B we have done, then C we have done. Okay, so through the B we have checked like E and D. Okay, but after that C is adjacent already traversed before. Then C part is done. Now E will be removed. So E, this adjacent will be traversed. Same things will happen. So there is no effect. And then D will be removed. Okay, D will be removed. And again, same thing. So all adjacents traverse. So nothing will be effect. No new node will be inserted into the queue. So in this case, this queue will become empty. And this loop will stop. Okay, so this loop is queue will become empty and this loop will stop. And now we are marking our visited dictionary. So where we are just maintaining our visited information. So that is visited or not. So that will become true. So you can see this is the input type of this, and output we are getting this true. All are visited. So in this way, this BFS algorithm is working. Any doubt in this implementation or this concept BFS? Okay, so this implementation got the concept. Once you got the idea of how Q is used in this, what is the purpose of Q to used inside this, you can write your way of the for the same things. So here is the main things. This is the this is how we are identifying the neighbors actually. So in list case, this is very constant space, like constant operation. We will directly face this information. In the case of adjacency matrix, this is a order of n operation actually. So that impact the complexity. Yes, someone speak.
Sir, not related to the BFS, but like as we are assessing that dot keys for the dictionary, like how is this information maintained? Like is it also done in the hash table somewhere? Like
It's the same hash concept is used inside the dictionary.
no, so for assessing the keys, because after we calculate the hash function, the initial input is lost now. So is it maintained separately somewhere or how? Like when we are
Okay.
assessing dot keys for a dictionary.
So what happened? So inside the dictionary, suppose if you are storing key as like this A, okay, this is you are making as a uh, uh, key, okay. So this is a key, and how this will be accessed in the constant stem. So that internal sum hash function, okay, internal sum hash function will generate a index for this, okay, at the store time. Suppose that hash function will work on some information on A, it will just generate a identity one index for this. Suppose that is like inside 102 to some information in the dictionary. And at that that other information is linked what is the key value actually. So that value is stored at that place, same place where this index is there. Okay, so now where at the time of storing of this A key, so this has your some hash function is generated a index where this stored. So you can see this A value is there, and this key value is there, and the corresponding value is there on this index. Time of searching, same hash function will apply on this A, and will check what are the index of this. So with that, after calculating the index, directly it will jump to that index and check what is the corresponding value for that.
So that thing is fine, but what I'm asking is, like, when we are doing is dictionary dot keys, that dot keys is assigning all the possible keys that are mapped to this particular addresses. So how are we? I means what's I mean, is
You
there
are
some
talking some specific function of the dictionary.
yeah, like dictionary dot keys that we are doing now in this BFS itself?
Dictionary dot keys, I am not sure about that function actually. Otherwise, dictionary is simple, na? So that creating any dictionaries, you can simply generate like this. So for
Can you
each vertex, huh?
can you scroll a bit up, please? Like, let me depict the line. Like, just stop.
Okay.
Like in line 22.
Mm-hmm. Ha.
I'm trying to relate this thing with hash that we studied in the last week. So I'm wondering, like, how this information of
Okay.
dot
So
keys.
what is this actually? A list dot keys. So this is returning a all actually all keys information list. Here actually we are traversing each. Suppose how many keys are there? Suppose we have 5 vertex, which is label 0, 1, 2, 3, 4. So this is like a linear operation. It will return all keys. Then we will read one by one each. So
Okay,
that
sir.
means we are identified that how many keys exist in our dictionary A list. So that is like a linear operation. It will check for each key. Okay, and for it will generate some sequence that is actually contain each key information, and then we are simply checking that uh, each value of this by traversing. Okay. Like this is just like a built-in function for the dictionary concept, so that will return only the keys value, all keys value as a sequence.
Okay, sir.
Okay, so here our operation is required to done on every keys, so that is the order of n. So this part we can consider the order of n operation if where the n is the number of vertex. Okay, but the searching and storing that information is the constant operation. Okay, in constant operation we can get the complete value details. So what value details we have, the total of that adjacent nodes. That information we will directly fetch in the constant time.
Hmm. Okay, sir.
Okay. So this is the implementation idea of BFS, and suppose the same concept we want to use with the adjacency matrix. So only this operation will be changed. This part, how we will identify the neighbors from the adjacency matrix. Because so okay, let's move to the previous part where the adjacency matrix is given. So that suppose this is for this is. Hmm. So as I mentioned that adjacency list direct constant operation, you can identify that here. Uh, you have to traverse all columns. Okay, suppose if you want, this is the label 0, 1, 2, 3, 4, and this is 0, 1, 2, 3, 4, and you want to identify that what are the adjacent of one vertex. So in this representation, without traversing each column, you cannot identify it, because for the one, so we are just looking for the adjacent of one, so we will look this row. Okay, so this one index row, but for this row we will check each value, which value is representing a one value. Okay, then we will only collect the all neighbor. We will check zero level, zero column. Yeah, this is one, so we will get a yeah one. Okay, so 1 to 0, yeah, 0 is a adjacent. Then next is 0, then next is 0, then next is 1. Okay, so this is 1, yeah, that means 3 is also adjacent of this. Then this is 1, so this 4 is also adjacent of this. So to getting this information, what are the adjacent of 1, we are traversing each vertex, each column of this matrix. So that column is also representing a total number of vertices. So that if number of vertices are n, so that means this identifying the neighbors is a order of n operation. Okay, so this is the only difference in the another implementation of the BFS with adjacency matrix. So you can see this adjacency matrix. So here we have write this neighbors function separately. Okay, that is passing the what is the vertex which we are looking for and adjacency matrix data, and then it is traversing each column and identifying that what are the neighbors for that and returning the neighbors. So this is order of n operation internally, and the algorithm is now same. You can see same things we are doing. So what here the input is adjacency matrix, same start vertex is given. We are maintaining the visited dictionary q, then implemented same while loop. Only the difference is this one. We are calling that function that is a order of n operation. In the previous algorithm, that was order of 1 operation, directly adjacency list. Otherwise, the same steps we are doing. Okay, so that also impact the complexity. So now this Priyansh.
Sir, we have to write this complete code in OPE,
You
or
have to
some
write.
part will be given.
No, you have to write complete.
Okay, sir.
If any additional task will be there, so then in that case, some that code will be given to you. But if your problem is directly depend on this, so in that case, you have to write complete. Okay, so yeah, this is the implementation for BFS, and complexity is also impacted of this, the number of edges here. So if we are using adjacency list, we are getting V plus E. Okay, is the number of vertices and E is the number of edges. So how we are getting this E? Actually, V plus E. So V operation we are doing this. You can see here also this is a one order of V operation. Okay, and after that, so here actually, if you look this, we are looking the each adjacent of each node. Okay, so that means if our graph have like A to that B is connected, then C is connected, and then B to D is connected, and then B to C is connected, like C to E is connected. So here we are just looking for each edge of each vertex. Okay, so that this information is representing like a number of total edge. So that means in the first case you are two edge. So this two edge information is representing two adjacent for this. From B, what are the adjacent of this B is like this D and C and A. Same number of edge, these number of edge. And C again the total number of edge which are adjacent of this. So that means we are working on the number of edge in this part E. And this operation is basically a constant operation. Okay, so here we are considering this part you can consider as a V operation, and this part is working like as a order of E, total number of edge operation. Because of that, we are adding these both term B plus E. Okay, but for the adjacency matrix, this neighbor operation actually, this initial part is like a order of V, but so this Q is actually maintained vertex. So it store each vertex in the queue at one time. So that means total number of vertex is V. So V time this loop will run. Okay, so this V time loop run, and for each vertex we will just call this function. For each vertex we will call this function to identify the neighbors of this. So that will become a V into V. For each iteration, this n of order of V operation. So V into V. That is become a V square. Okay, so here in this way we are looking at complexity for this. So this identify the neighbors actually impacting the complexity in the case of this adjacency list and matrix. Okay, so now the next thing is the some related algorithms for this. So now BFS, if you have done, we can just modify little bit these algorithms and just we can identify other information. So like the next implementation is given, find parent of each vertex BFS. So when we are traversing from A to like B, B, C, D. So on B, C, D, we are from coming actually A. Okay. So at the time of our implementation, we can store this information B, C, D. So where from we are coming. Is some small modification at the time of traversing. We will when we will traverse all the adjacent of nodes, we will maintain the parent of B is A, C is A, parent of D is A. For parent of A will be considered like as a -1. Okay, so that is no parent. This is the starting vertex. So some small modification, same type of algorithm is there. So or all so this is find parent of each vertex using BFS. Parent and one is equal to. Okay. Determine shortest path from vertex. Okay, so that okay. So this is one application of the BFS. If suppose sometimes shortest path is asked in the terms of minimum number of edge or minimum number of vertex in the path, not the weight actually. So suppose we are looking that what is the distance, shortest path distance from A to any vertex. So that will come like as in, so we are getting the in tree, each we have the path from root to each node. So what is the that distance in the terms of number of edges, number of vertex? So that we can also identify that based on this information, parent information, or we can also maintain the level. Okay, so this if this vertex is traversed at this 0 level, so the next level is like is a 1. So we can maintain the level information also to at this labeling of the traversing. So that is actually some modification is there. So otherwise most of the things are same. So you can see at the time of visiting false, we are setting our parent equal to -1. Okay, each vertex. And after that, so okay, so we are initializing the first vertex into the queue. After that, at this time, this is the same algorithm, nothing changed. Only at this time when we are just looking the adjacent vertex and we are inserting that into a queue, we are also storing this information. So parent of this adjacent vertex equal to current vertex. Okay, so when we are traversing from A to B. Okay, so when we are looking for the B, so B is now adjacent vertex of A, and this is a current vertex. So at the time we are storing this information. So what is the parent of B is A. So that we are maintaining, and then we will get another information. Who is the parent of? With the help of this parent, we can identify the path. So label number. So that label number we can also identify that by some little modification in the same type of code. So we maintain this label each vertex initially -1. Then we are assigning the label 0 to the start vertex. Okay, this is the starting vertex. After that, we are updating this label information once our task is done. Okay, so for each adjacent vertex, we are looking the what is the label number of the parent vertex actually, and we are incrementing by 1 in the same loop. Okay, so if A is traversed, we mention it's the 0 level. When we are traversing all the adjacent of this, so B, C, D, we are looking for B. So at the time of B, we will check what is the parent index, that level number 0. So we will add the 1 here. Okay, same for C. What is the parent of level is 0? So that is 1. What is the parent of 0? This is 1 here. Next time, what are the adjacent nodes for B is? So that we will add from the parent level value y1. So in this way, you will get a level number for each vertex in the traversing. Okay, so say that information you will get it by this modification. So these algorithms discussed in different lectures of this week, so that have some additional information by some modification. Okay, so now the comes to the DFS algorithm. So the okay, so I idea of the BFS is clear. Any if you have any doubt or You can ask. Yeah, no.
Sir, is there any situation where using the BFS with adjacency matrix is useful than adjacency list?
Yeah. Oh, useful. No, both algorithms are doing the same task. They are checking the connectivity or traversing information. So I think in the terms of efficiency, that adjacency list is better data structure. I'm not sure that there is any advantage for the with that adjacency matrix for the BFS. No.
So we don't need to basically learn both, or we can go with the adjacency list if we have to basically learn one thing.
No, but you should know actually. Suppose if in the if question input is given adjacency matrix, but if you're not learning how it will handle, then how you will do?
Yeah, sure.
Task is only the identity, as I mentioned that only identification of the neighbors. That task is changed in the this implementation. How we are identifying the adjacent of any vertex. In dictionary,
Sir,
in adjacency list, this is very straightforward. Huh? Yeah. Okay.
what if our graph is dense graph? Like we have a lot of edges, a lot more like highly connected graph.
Uh-huh. So what your question is?
So I'm saying like if we have like highly connected graph, then it will not matter like going with from this linked list will have more will take more time. Will have more time complexity, I think.
Why it will take more time?
Look, like if I consider it's like a completely connected graph. So
Huh.
there's like n into n minus 1 by 2 edges that I have to transverse. Uh, or like it's going to be n times n minus 1 edges that I have to transverse.
Mhm. But
Uh,
in this case also, that will not equal. That will be equal to the like matrix information.
mm,
Things at the time of identifying the neighbors actually. Okay, so in the complete graph, so that means one will contain the all like 0, 2, 3, 4, 5 vertex are there. Okay, so, same vertex will contain all the edge, remaining edge. This type of information is there, and same matrix is also contain 1, 1, 1 each vertex like this. Okay, so here what task is there? Uh, we to identifying the adjacent nodes, we are calling the process and we are checking this process actually, checking this process, and after that we are getting that these nodes are the adjacent of this. So this additional task with the adjacency matrix, but with the adjacency list we are getting this information in constant operation. We are directly getting the all neighbors in one operation. Here we are getting this information in order of n order of v operation. After that we are doing the same task, we are traversing each neighbors, so still have the additional cost.
Sir, in the second thing, we are storing this as a form of linked list, not as a
No, no,
continuous.
not a linked list. So here we are implementing this with the help of a dictionary.
Okay.
So dictionary
No,
will return
dictionary, the
the complete.
values.
A dictionary value is representing as like this. This, so this in this actually complete list will be we will get this complete list in a constant op. Okay, but here we are creating this list. Actually, we are creating this list in by this order of v operation by checking the process. But this is already
Yeah.
available in our data structure. So this will be fetched in the on constant operation. After that, we will just traverse each node for our process. Okay. So still, maybe the complexity will become approx equal, but still this have the additional cost.
Okay, sir.
Okay. Okay. So now moves to the next DFS. Huh. So the idea of the DFS is different for the same purpose. Okay, so DFS, according to the name of this, depth first search. Okay, so that means if we are traversing any node, we will check the adjacent of that node. But after moving to the adjacent, we will not complete the all remaining adjacent here this time. We will check the next adjacent of that. So that means what are the possible depth, we will complete that depth first to traverse. Suppose if we have graph like this, so A, B, okay. So and we are applying this from here, this algorithm. Okay. So this algorithm traverse A first. Then it will check any of the adjacent of this. Okay, so suppose if it is picking B first. So if we are B, so again we will check what are the next node is connected to the B. So that means we are entering into this depth and complete this depth first, where till the last point that we can reach actually. So what are the next node is connected through the edge adjacent. Okay, so what are the, suppose if it is moving to this D part. Okay, so that means next node is traverse like is D. The same things from D, from where we can move. So D we can move E. Okay, which is not visited. So here also we will check which is visited. Only that side we will move. So E will be traverse. From E again same D and B are adjacent, but F is not visited. Okay, so we will move to F. Now you can see this depth is completely finished. Now there is no node to traverse. Okay, remaining. So now there is no choice. Then we will come back, okay, to the previous node, and we will check is there any another possible path from this. If not, then we will come back. Then D. If any other possible path from this, okay, no. Then B. Then no. Then A. From this point, there is another adjacent remaining. So that means we are coming back to the previous node one by one and checking the another depth. Okay, and we are getting the another depth from A, that is C. So C. So we are getting same here also. We will get a tree, but different type of traverses. So this is like A, then B, and then D, and then E, and then F. Okay, after reaching the F, we are moving to the previous node and checking the another adjacent for this if it is any remaining. So in this way, this will return back to the A, C. So this way traversing will done in this process DFS. Okay, so according to the name, we are not maintaining the level wise. Here we are following the depth wise. So first we will complete the depth and then we will return back to the another depth, possible depth. So traversing will be done like this. So this operation can be done with the help of stack. Okay, so stack properties first LIFO, last in, first out. So that means we will, so in this case, for this graph, suppose if we are traversing A, then what are the adjacent of A's? So that is B and C. So we will store this information into a stack. So suppose we are maintaining B and C in the stack like this. So we are inserted this. Now the removal will be performed from the top. Okay, so B will remove first. And what are the adjacent of B is D and D. So we are removing this B. Then next insertion will be look like this. So C is still there. Now the insertion will be happen like E and D. Okay, like this. Again, next removal will be done from D. Okay, so D is now removed. So that E is next node. So that we will just insert E again. Okay. Okay, so E is there, and again we will, because E is still traverse. So in this case, multiple insertion is possible in the stack, because if our E is not traverse, again we are getting from D, so that again insert. Okay, so that again we will remove E. So at the time F will insert instead. Okay, so F E C like this. Then F will remove. Then there's no adjacent. Then E will remove. Then we will move to C again in this case. This type of traversal will maintain by the external stack you can use, or you can use a recursive DFS. So recursive DFS internally use the same stack things. So we are calling the DFS on this node, and we are calling the recursive DFS on the one of the adjacent. Then the same algorithm will call again the DFS on the one of the adjacent of that vertex. So in this way, the we will reach at the base case, and then we will move back to the moving to the next adjacent. So this implementation can be done by the both recursive approach or external using. So this is a conceptual question also, which data structure we used for the DFS, which data structure we used for the BFS. So just remember this: DFS for the stack, and BFS we used for the queue. Okay. So this is the basic idea. So same type graph question may be there. So just validate your that options with the graph that your algorithm is completing the that depth first. Okay, by just validate the answer. So just remember this concept for the traversing. So that will solve the question. Okay. So yeah, so the one question, so similar type of question in the activity assignments are there. So if traversal tree, then which edge is possible on this or not? So in this case, edge is not possible like it's a cross edge. Your tree have some this type of branch like B and C, this type D, and this E, and suppose this is F. Okay, suppose this is the DFS traversal. Then this is the tree generated by the DFS traversal. So in this case, edge is not possible between two branch actually of the tree. So here, if we talk about F and C, so F and C is not possible. Suppose if we connect this F and C in the original graph, so C cannot be come into the another branch. That C should be come in the same branch like this. The DFS, so that if F and C is connected, so that definitely the C will be connected to the F in the same. So any cross edge between different branch cannot be possible in the original graph. Just remember this for the DFS tree. BFS we have label difference cannot be more than 1, but for DFS tree the S cannot be connected on the different branch of the traversal. So here this is possible, B and F is possible. Okay, so this is the one possibility, and A and F is possible like this, but this is not possible. B and C is not possible, E and F is not possible. Okay, D and C is not possible. So different connection is not possible. Okay, yeah, so this okay. So yeah, in the notes, this visualization is also given, okay, on the GitHub notes. So you can also utilize that. Yeah, Anurag.
Sir, can you please repeat the last part of that? What is not allowed?
Okay. So one of the activity question, I think, move to this graph, BFS, DFS. You can see this graph. So here what we are giving the DFS traversal. Okay, so DFS traversal tree, which is rooted 1 for this any undirected graph. So we are getting this type of traversal by the DFS algorithm. Now we are checking that which edge is possible in the original graph. So I'm telling you any cross edge between two different branch of the tree. Okay, so this branch means so here. So this is the separate branch. Okay, this is the separate branch between two separate and this is separate. Like this is the separate branch. Okay, so that means S cannot be possible between two separate branches. Like 5 and 6 is not possible. Okay, 6 and 3 is not possible. 4 and 5 is not possible. So what is the meaning of this? If our original graph contained this 4 and 5, so this 5 cannot be come into the different branch in the tree. So if 4 and 5 is connected, so at the time of traversal, if we are moving to 4, then this 5 should come on to below of this if this is connected in the original graph. Because we are moving the depth-wise traversal. If 4 and 5 connected in the original graph, so 5 will definitely come below this. It cannot become separately. So this is the validation to check the cross edge between two different branches is not possible in the DFS table, in the original graph. DFS tree. Okay.
Okay, sir.
So,
Thank you, sir.
so this type question you can remember.
Sir, same for the BFS also.
No, BFS was different. As I mentioned that BFS, if the level difference is greater than 1, then that edge is not possible. If we are looking for any edge like u comma v, so check what is the level number of u and what is the level number of v in the traversal. Okay, and check the difference. What is the difference? Absolute difference. That should not be 1. If it is greater than 1, that edge is not possible in the original graph. So that is the validation of BFS tree.
Okay, sir. Thank you, sir.
Okay, level means this thing. This is coming at the 0 level. This is coming at the. These are coming at the 1 level. These are coming at the 2 level. These are coming at the 3 level, like this. Okay. Now, if we are looking for 7 and 3, this is possible or not? So just check 3 and minus 1. This difference is coming 2. So this edge is not possible. But if we talk about like 6 and 3 possible, yeah, 6 and 3 possible. So if the difference is 2 minus 1 is 1. That is possible in the original graph. So that means if an original graph contain any edge between 3 and 6, still you will get type of traversal. Okay, that will not impact. Okay. Okay, so this is the implementation of the DFS. So this is additional stack with the help of additional stack. So you can see we are using stack this time. Now same things we are doing, but case of Q we are using the stack this time. Okay, so we are maintaining. Initially we have set up the false for all. Now we have created the stack, push the starting vertex. Suppose we have the graph like this: A, B, C, like not like this. Where is the rectangle? Like D and E. Okay. So suppose we have this graph. So initially step is false, 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 false. This is the visual information. Okay. After that, we are applying the DFS on this. So we are just setting that we are pushing this into a stack. So we are maintaining one stack and pushing into our stack. Then we are repeating the same complete process until our stack is not empty. So for this, we are just removing this from the stack. So that is the pop operation. Pop will always remove from the top. So that current vertex we are getting that A, okay, in the first one. And then we are looking if this current vertex is visited equal to false. Okay, if this is not visited, okay, this time, then we are marking as a true. So this time we are not marking this as a true at the first step, but you can change the implementation according to your need. So in this implementation, we are marking visited at the later. So when we are removing from the stack, we are marking as a true. Okay. After that, we are pushing all the adjacent of this into our stack. So this is the part for each adjacent. So you can see this is the direct same neighbor information we require. We are fetching this information and insert. We are pushing into our stack. So what are the adjacent of A? That is B and C. That will push into the stack. So like C and B. Any order you can maintain. Okay. So in the next iteration again stack empty. So one will be removed from this and we will mark as a true for this. So that means initially we mark this as a true and then now we are checking this is marked as a true. And same things will push all the adjacent of this D and D. So this is removed. Now next level that E and either E or D in this. Or you can also maintain E and D conceptually. Both are correct. So insert. Next and D will be removed. So D will be marked as a true. So that will become true. Yeah, please. Yes, Sambhavi Verma. Yeah, please ask. Left. Okay. So D is now removed. Now we will, when we are removing D, we will insert again E. So E will insert. So now E will traverse. Next, this will traverse. So you can see depth is completed first. Then we will return. So you can see next E is already traverse, E is traverse. All will be removed. Now we will move to the C. So at the last, we are checking no adjacent, then C will traverse. So this process is happening with the help of stack. So implementation is very similar. Only the thing is we are using stack this time, and we are maintaining our traversing process by just marking this instead of things. So same things you can do with the adjacency matrix. Okay, so this is the another way of the implementation of the same DFS with the recursive way. So this is not very different. So this is as the professor have discussed in the lecture, this implementation. So you can see same things visited. So this is the visit. Okay, so initialization is done by separately. Okay, so in this implementation, we have called this init for list first. So that is some setup is done. So that visited parent, all this information is set up by this function. And then we call this DFS, and then we mark this first node as a true. And after that, we are calling the same recursive function on the adjacent node. So if you can see each adjacent node, we are checking if not visited, we are marking it, and we are calling the same algorithm on the one of the adjacent by this iteration. So this will move to the same depth wise. It will move to the last depth, will return back this call internally. Okay. So any algorithm which you are comfortable, if you are comfortable with recursive, that's fine. Otherwise, you can without recursive. Okay, with the external stack. So both are the same, only the implementation difference conceptual wise. So this is another version of this. You can ignore this because here we are just maintaining the global information. So this is just another implementation. Same implementation we can do with the adjacency matrix. So you can see the here neighbors. So the difference is only this neighbors function. Otherwise, the same things are there. Okay, so we have set up this innate things. Same recursive calls are there, but call this neighbors we are getting by this function. Otherwise, the implementation is approx same. Okay, so same the adjacency list. Only the neighbor function will change. So this type of implementation you can ignore. This is just only implementation, only the global data. Okay, so that is no need to focus. So just only focus the main algorithm of the DFS, and if any modification is done for the additional information. So now these are the both basic traversing algorithm. Some that application we can identify with the help of this BFS and DFS. So that our first is connected component. Okay, because this so these application you can identify from the both, either from BFS and DFS. So find component means you are looking that if you are starting BFS or DFS from any vertex, are you able to reach to the all nodes or not? That means all nodes are traversed or not. So just apply the same BFS algorithm and check your all node marked visited equal to true or not. If not true, that means your graph is disconnected. So we are just getting some other information by the same algorithm. So finally, our output is looks like this: true or false information by the BFS. So after one run of the BFS, and you are any vertex visited value equal to false. In that case, that means that graph is not connected into that. Okay, so that is identification of your graph is connected or disconnected. Other information that you can also identify that how many components are there, connected components are. So suppose this A, B, these are the one, C, D, and E. This is another component, and F and G, another component. Suppose this data is given like this, okay, disconnected graph. So what will happen? You will apply a BFS algorithm until your all vertex not visited. So in this way. So first BFS, suppose if you start from this A, okay, and after applying the BFS on A, you will see how many vertex are visited by the one run of the BFS. So you can see this will be true, this will be true, but other will remain false. So what are the remaining nodes are there? You will apply a BFS again on the any another remaining unvisited vertex. So BFS on this. So by BFS on this, so this will become true, this will become true, this will become true. But still these will not true. So again apply the BFS on the remaining vertex F and G. So then you will make it true. So how many times this BFS is called actually to perform all the visited things? So that is just also represented number of connected components. So you can just maintain a counter that how many times you have to call this function, okay, during the complete traversing on this graph. So that is represented total number of connect components in the graph. So you can just implementation. So we are maintaining this information component. We are maintaining component ID. We are maintaining, but in this is the main actually logic for this. We are just looking scene is less than equal to max. So we are maintaining one counter that how many vertex total we have in this graph. Suppose 10 graph we have. Okay, in set equal to scene equal to 0. So this scene is representing like how many vertex are visited. Okay, and we are running this while loop. So suppose in the first run when we are applying the BFS on one vertex, and suppose 2 is marked as a visited. 2 is marked in the first run, but still 8 is. So this 2 is this is the 2 and this is the total vertex 10. So that means still we have the vertex which is not visited. We will apply the again. We will identify that which have the less. So that means component ID is still -1. So based on that, vertex are not visited yet. Okay, so that just identified that again and again apply the BFS. You can see again we are applying the BFS inside this. So check again how many total vertex are visited now. So this increment the scene value and just run again. So this while loop is basically is representing the total BFS. How many times BFS we are applying on the each components. At every time we will increment our component ID by 1. So that is representing the total number of calls iteration of this while loop. So that is the identification of total number of component. Okay, component ID. And each time we can also maintain that which vertex is coming within which component ID. So we are maintaining the ID like when at the first time we are maintaining this is coming as the one ID. This is second time this is the second component. This is the third component. So this value we are maintaining by this. So these are some additional variable information you can maintain in the same type of implementation by some small modification. So this is one task. Pre and post numbering using DFS. So that is also one another way to identify type of edge actually. So with the DFS here we are applying. So this algorithm is using the DFS concept, but in this algorithm we are maintaining two type of counter, pre and post for the each vertex. This count value. So with the help of this, it will generate a pre and post value for the each vertex. So at any time when we are visiting, so if we are starting from this vertex A1, so this will check what are the adjacent. Okay, so we will start and we will maintain the pre value for this. At any time when is entering into this vertex, so pre value we will set like as a 0, and then we will move to the next call. Suppose we are moving to this, so this now set for the 1 like this. Okay, so at the time of depth level, what depth level we are moving, that pre value will be increment, and the return time we will just increment our post value. So like this is 2, and from suppose if we are moving to this, then it will become 3, and 4. Now it is completed. So now we will increment the post value. So here from, okay, so that post will become 5, then post will become for this vertex 6, then post value will become for this is 7. So okay, so pre at the time of end, like when we are to the depth, and post value will be increment at the time of we are returning back. Okay, so in this way, this value will be identified. Based on that, we can identify some information like what type of edge is actually there. So this is the, you can remember that for based on this pre and post numbering for each vertex, you can identify that what type of edge is actually that. That is tree edge, or that is cross edge, that is back edge. Okay, so in DFS traversal, you always get some tree like this. Okay. Okay, so that trees contains only the tree edge, but some edge which is not included in this tree, so that is comes under the back edge category or cross edge. So you can also identify that back edge and cross edge. And back edge is actually also written one information that cycle. So if any edge is that means your graph contains the cycle. So that is the identification. So suppose if you have one edge UV, and if interval is the pre-value of post value of U. Suppose this pre-value of this is 1 and this is like a 5. This is 4. Okay, pre and post is 3 and contain this 2 and 3. Okay, so that means what is the range 1 to 4? So this 2 and 3 value are coming in this range, in between. So if this condition is true, so that means that actually tree edge. If this condition is true, that is represented as a back edge. So that means pre and post value. So this value is coming between this range. That edge is back edge. So this is also your identification of cycle in the graph. So your algorithm can identify that graph contains a cycle, and this is a cross edge. So just remember these formula. These are also important if pre and post information is given. I think some activity is also given on this. So that is some application. Okay, now only this DAG is remaining. So first thing is what is DAG actually? So DAG is basically a directed acyclic graph. Means this graph not contains a cycle. Okay, and this is a directed graph. And this is this requisite for this okay, topological sort or this problems. We should have the input and DAG. And there are many interesting can be generate real life problem can be generate for this type of information, DAG information. So this is the first thing you should have the good understanding of what is the DAG actually, and then topological sort. Okay, I'm not sure. So already 2 hours is done. Okay, do you want to continue or want to discuss this in later? Anyone?
So can you go like DFS code once more? Like just wanted to understand one line in that code, the first code for the DFS.
BFS, the application. Matrix 8. This one. No?
So the first one, the first code.
External stack. Hmm.
So in this, like in line 35.
Line number 35. Okay.
What I'm thinking is like we are doing this in line 35 that if visited is the false, but in line this 39 we are already checking that if it is not visited then we are pushing it in the stack. So cannot we skip this line 35 it's all together because as we are like checking this condition in line number 39.
Okay, 1 second. So line number 35, we are looking that if this vertex is not visited, then we are marking this. Okay, so this is not true. So this is for marking that marking vertex. Okay, you are saying that if
I can just mark the current vertex and go ahead with the rest of the
hmm,
course. As in the line 39, I'm already checking. If it is not visited, then I'm pushing it in the stack
okay, stack,
in line
okay.
39.
Okay, but this is for the adjacent now.
Hmm. This is for the list, adjacency list.
Adjacent vertex, and then this is not okay. They're not visited. Then we are stack. Okay. Yeah. So that means stack all contain always the visited things. Okay. But there is a chance now. So as I mentioned that any vertex can be come more than 2 times. Maybe in the first process that is marked as a true, but still that is exist in the stack. So in this example, so like this. Okay, so
Uh,
we inserted this. Huh?
so that thing is taken care of in line number 39 now. That is
So
if
that okay,
not
okay, 1 second. So here you see in this example A, when we are looking for the A, we are inserting B and D, correct? So at the time, B and D both are not, sorry, B and C both are that visited. So we have inserted B and C, correct? But at the time of B, you can see we are just at D and E both are adjacent of this, but still D and E both are not visited. So our algorithm will insert this.
yeah, it will pop out B and it will
Uh,
insert like
C,
C.
D, and E, correct?
Yeah.
But now we are looking E. So still you can see this E is not visited yet. Again, it will insert.
No, yeah. It will if current vertex equal to. Hmm.
Correct. But when we will remove this E, so at that it will mark as it true. Visited mark equal to true, but still it is exist in the stack again for the next time. At
Hmm.
that time we have to verify it is already visited or not, because there is a multiple entry in the stack is possible in this implementation.
Okay. Hmm. Got it. Yeah,
Okay.
thanks. Yeah, thanks.
Yeah. Okay. For this DAG, actually, I'm not sure you are getting the all things right now or not. So shall we cover or what should do, or should we discuss later in any other lesson? Oh.
We'll stop here, sir. We can continue next session.
Next session or otherwise revision session, we will consider this. You can just try to understand what is this deck. I am just giving the idea of this. So topology, what? And the concept is so okay. Suppose this is a topological. Okay. So the working logical sort is like this. So we identify. So this is like a DAG. Always we will get the input as a DAG for this topological sort. After that, for algorithm, what algorithm is doing? Algorithm is identifying that which node has the in degree 0. So this is the first step of the algorithm. So first we will calculate all the in degree actually for the each vertex. So what is the in degree for this is 0. What is the in degree for this 2 is now 2. You can see 2 edges are coming on this. Same things. This is 0 also. So for each vertex, first step is to identify the in degree. And after that, what we will do, we will pick the vertex which have the in degree 0. Any vertex. Okay. So suppose if we have more than vertex which have in degree 0, then we can pick any. So that is the first vertex we will select. But after selecting this vertex, we will remove all the information, all the that connection from this. So that means we are removing this completely. So 0 vertex and what are the edge are connected from this. So that all information we will remove. So so this 0 is now the first vertex as a that in the topological sort, then we will remove this. But if when we will remove this, it will impact the in degree of. So, okay, so suppose if we are removing this 0, so in degree of 2 will reduce by 1 because one edge is now removed, this edge, okay. So this will reduce by 1. So that means after removing vertex, when we are selecting the vertex and after removing this, we will update our in degree. Okay, so what update we will require? So what are the adjacent of 0 that actually in degree will be reduced by 1. So we will reduce the in degree of 2, we will reduce the in degree of this 4, we will reduce the in degree of this 3. And again, we will repeat the same process. Okay, we will identify that which node has the in degree 0. And then we will select any one of them. Then we will from that, and then we will update again the removed node adjacent vertex in degree by -1. Okay, so this algorithm is working. So identify the in degree. So if you see this overview of the implementation, so Q we are using here. You can see in degree we are maintaining and topological sort list we are maintaining. So in degree we are setting initial as a 0 for that. Then we are computing the in degree vertex now. And after that, we are setting this find the vertex with in degree 0. Okay, we are identifying that which vertex has the in degree 0, and we are putting all these vertex into the queue. And then we are getting one by one from the queue. Okay, and we are adding all the vertex which have the in degree 0 into the queue. So in this process, so we are just maintaining this, remove one vertex from the queue which have 0, and that become a current vertex. After that, we are appending that vertex into the final sorted topological sort, and then we are reducing this in degree of this vertex by -1. So this will become a -1. Okay, so 0 to reduce by 1 -1. So that we will not consider again because that is now will be considered as a. Okay. But after that, we will update all the adjacent vertex in degree by -1. And if any degrees become 0 after reducing this, that we will insert into the queue for the next process. So now this is the repetition of the iteration, and this in this way you will get a order. That order you are getting, that means first we identified the 0. So after updating all these things, we are getting this in degree 0 for 1, then in degree 3. So this is the implementation of the topological sort, but the conceptually there are multiple many that question may be asked, like suppose if graph is A to B and A to C, and like C, this is the direction, then D and E. Sorry, like this. Okay, so suppose if this graph is given, so what are the topological order possible for this? So initially you can see only A contains the 0 in degree, so A will be the first vertex. Okay, once so 0, 1, 1 and 2, this is the in degree person. Once we will remove this, so this will become 0, this will become 0. Now you can pick either B or either C. So that actually represents the total number of possible topological sort. So if suppose if we are picking B, so when we are picking B, if and then we will remove this, so this will reduce the degree of D by 1. Okay, so this will become 1. So that means you cannot pick next D, still that have the in degree 0, but next level you have to pick C because C has the in degree 0. Then after removing the C, so D will also become 0, so that last is D. Okay, so this is the one possible order. But after A, you can also pick C because both have the in degree 0. So if you are picking C, then removing C, only the B is available in degree 0, so D will come. Then after removing B, then D will come. So two different possible sort is available: A, B, C, D, and A, C, B, D. Okay, so for this input, both are valid topological sort. So this type of question generally asked. So like this, which one of the valid topological sort order and how many possible topological order of given graph. So you can identify like this in this way. So that is the possible question. And a similar, just some another version of this topological sort is just the longest path in DAG. So this algorithm. So that actually provide the another information. So that actually provides, so same for same graph like A, then B, then C, then D, and okay, suppose the same graph. So same type of topological we will, but this time we will identify that how many like distance we have like removed to all this. So suppose at the first time, so at the first time we can only remove this, okay, because this have the integrity 0. Now next time after removing this, both will become 0, okay, B and C. So that means first time A can, second time B and C both can remove. Okay, so after removing this, next third time this will 0, and so this third time this T will leave. So total 3, actually this is called as the longest distance. So 3 is the distance. Okay, so this type of question is generally asked for like this. So suppose if your courses and where the prerequisite is there for the courses, so how many minimum semester is required to complete. So in the one semester you can do this, second semester complete this, all B and C, third semester you can do this. So total longest distance is 3. Okay, so in this modification we identified that after every modification remove what others we can select. So we will just so next level we can modify this, we can remove these levels. So we will remove all these, then we will check on the next level what we can remove. Okay, so we will identify that how much steps are required to remove all. So that is the last, this longest path in there. So yeah, this 3 is the distance. So this is the basic idea. So the same things we are doing, but only we are maintaining this time this longest path information with the help of this. So just look some I have added some slides for this. So just look how it is working, this topological sort in DAG. Okay, so step by step process is given. Just run this and see how it is working. Similar is longest tag. Okay, so how this is updating the data. Yeah, Anurag.
So could you please explain the maximum part used in the code for the longest path?
Maximum means okay, so 1 second. Okay, so as I mentioned that suppose we are just creating a problem where codes are given. Okay, so suppose this we have the DAG like A, B, C, D, okay, and E, and F, and G. Okay, suppose this is the problem, like all these are the courses. Okay, so that means all these courses have the prerequisite. So it's actually like this. Okay, like so what is presenting actually? So that means we can pick so in one semester we can pick any number of courses which have no prerequisite. Okay, so this type of information will be given. So here B has the prerequisite A. So that means we can only pick B once A will be complete. We can only pick C, but we have to complete A first before this. Okay, so this type of information is given and it is creating a DAG. So, and we need to identify that the problem is like this. So how many minimum semester is required to complete all these courses? So this longest path in DAG, this implementation, we can identify this. So in this implementation, we are looking the same things. What are the nodes which have integrity 0? Initially, you can see 1, 1, 1, then 2, then 1, then 2. Okay, this is the information of integrity. So in the first step, how many courses I can pick? I only this one, because this has the integrity 0. So in the first step, I have picked this A. Now, once I have completed this, I will remove all the information of this. So now all this becomes 0. Now all integrity becomes. So next level, this B, C, D has the all 0 information. So that means I can pick all these 3 in the next term, next semester. So like B, C, D, I can pick because all course has no prerequisite. Now, if I all finish So all this in degrees removed now. So this will become 0 and this will become 0. So all dependency will be removed. So now third one, so I can just pick this E and F. Okay. So once I will finish this, so this dependency will be removed and this will be reduced to 0. Now I can pick in the first this G. So this is representing longest path distance actually. So this the value for the longest path. So that means that this is representing a maximum paths possible in this DAG. Yeah. Yeah, please ask a query.
Sir,
Yeah.
then what is the difference between BS shape and this longest path? Because in the BF shape also we did the same thing. We have
But BFS,
sorted.
but there is no dependency that DAG requirement is there. Okay, no. But here DAG is requirement is there.
Okay.
Not just checking that in degree or this type of information for the BFS implementation. But here we are looking that can only pick the nodes if that nodes have in degree 0. Okay, but BFS we are not looking like any this type of information. So here the prerequisite is the graph should be a DAG. Then we can identify this information.
BFS means shortest path, right?
No, BFS means is not shortest path. The BFS is a traversal algorithm that traverses all the nodes, but BFS provides the shortest path in the terms of minimum number of edge or minimum number of vertex in the path. So suppose if we have graph like A and B and like C and
In the same graph, could you please explain the upper one?
So that is the DAG actually.
Okay.
Okay. So suppose if we apply the BFS on this A, okay, so you will get a similar type of structure like level will be B and C and then D. Okay. Now next level from this is B to E. Okay. And now D to F. This. And then suppose if you're calling E, then G. So this tree will come actually. So here this is also representing a shortest path from A to G or A to E, A to C, A to F in the terms of minimum number of path in minimum number of vertex or minimum number of edge in path actually. So if we count this number of vertex, so what is the distance actually from A to F? If we are counting the number of vertex, so this is 3. Okay, so A, D, F, 3. So this is the different information. Okay, this is the different information. Yeah, you can just so for this graph you can just understand that like this. So if you find out that what is the max after getting this G, what is the longest path actually? So this is the longest path, and this contains the 4 vertex. So that equivalent to your this information longest path in DAG for this DAG actually. But this is a traversal algorithm that returns a shortest path from the start vertex to the another vertex in the terms of number of vertex in the path. Okay, here we are not considering any weights or any edge. So that shortest path is algorithm is different algorithm which we will learn in the Week-5.
Okay, got it, sir.
So, but this longest path we are looking only the longest possible path in this. When we are just following this process by just picking the 0 nodes every time. So what is the longest path? So there is a prerequisite here. The graph should be the DAG, but there is no prerequisite for the. Okay, yeah, Anurag.
Sir, in the implementation of the this longest path, there is a code. And that, sir, like after we reduce the end degree for the vertex, we are applying a maximum part where we use the distance of the u and 1 plus the distance of v. So could you please explain me this part?
Okay, so that you have to, yeah. So that if you want to understand this, now, so just run this. So same way how we are just taking this. This is just a maintain to actually this longest path distance. So we will okay. So I have to explain the every step then. Huh. Suppose we are running this. So at the starting vertex, what are the in degree of the each vertex? So you can see initial in degree is the 0 for 0 and 1 in this graph, correct? So here you can see what how the data is actually handled. So this 0 and this one, first step. So now when we are just moving to the next step, okay. So 0 we are selecting. So after selecting the 0 vertex, we will identify the L path uh, for the in this step. So we will also inserting the 0 degree nodes into the queue, and also we will identify the L path for this. So that will be updated. Okay. So after removing 0, what is the longest path for this? You can this is for 2, 3, and 4. But there is a chance in the later that this longest path which you are getting from after removing 0, getting this 111 some longest path from 0, but later there is a chance that you will get this value less from any other another vertex. So because of that we identified that what is the previous longest path value and what is the current longest path value we are getting for any nodes, and we are selecting maximum one in the algorithm. Okay, so there is a, so this is impacted from 0 that 1 when we remove 0. Okay, so this level for the vertex 2 is now updated from when we remove 0, but that 2 may also be impacted if we you can see if we are removing this 1. So again you will get another label path because the 1 also contains degree, so you will get another label path distance from this one. So every time we just identified that previous level is the maximum and the current updated one is the maximum. So we will pick the maximum one because our target goal is to identify the maximum here, maximum long. Okay, so because of that, this algorithm is doing this thing. So in this part, this is the in degree, and after that we are just fetching the in 0 degree DQ in degree, and we are reducing of this, and for adjacent of this, each current vertex we are just reducing the in degree, but label path we are updating by maximum of the current label path, what is the which is already there, and what is the new L path which is current L path of the current vertex plus 1. Here adjacent vertex you can see this we are picking previous one, and this we are picking the current one plus 1. Okay, so what was the value of this and what was the current updated value from this? So which one is the maximum that we are selecting? Okay, so that because that field is changing by from many value actually, by from we will just so many edges are coming from for that vertex in this graph. So like so in this graph you can see this suppose this 5. Okay, so 5 L path value will be actually edge is coming from 2 also, edge is coming from 3 also. So every time this L path value will be updated once we will remove this, but from which update we are getting maximum one, so that we will actually maintain. So always we will just check that previous one was the maximum or current one was the maximum, that we will update in the final table. And after completion of the all process, then we will pick the we will select the maximum all. Okay, so that will represent this information. So just go through the step by step for any input graph, then you will understand that how it is required. But the goal is the same actually. Okay. Yeah, any query? Yeah, Anurag, it is clear?
Yeah, yes, sir, got it, sir.
Okay. Okay, any other query? Or shall we close already? Over 30 minutes is done. Okay, then if no query, then I think we can close the session. Thanks, everyone.
Thank you so much, sir. Good night, sir.
Good
Thanks.
night.
Thank you, sir.
Thank you, sir. Thank you.